Hi everyone, I'm Khooyooz from Heidelberg University Eclectics team. Today I want to present my recent paper which has been accepted in EMBC conference 2025 Copenhagen. My paper is entitled IDNoise, Resource-Aware Machine Learning-Based Noise and SNR Detection in Electrocardiogram Signals. So the outline of this presentation is an introduction to wearable healthcare systems, the dataset that we have used for training the algorithms, methodology, results and discussion, and we finally conclude the paper. So here are some abbreviations that I have used during this presentation. And the wearable healthcare systems application is for continuous health monitoring of physiological and non-physiological parameters for an early detection of health issues. From the global market point of view, wearable technology, as you can see in this figure, in year 2025, $94 billion has been invested in the market for wearable healthcare technology, and with an annual rate growth of 14.6%, it is projected that in year 2032, $231 billion will be still invested in this market. As you can see, the most used type of wearable devices are wrist-worn devices. But designing the wearable healthcare systems has several challenges. One of them is data. Data quality in terms of accuracy and reliability, and also data privacy and security. So if the quality of data is poor, we would have false alarms in the wearables. These will cause anxiety and stress for the user and probably cause wrong intake of medications, and in the long term it will cause loss of trust and reluctance to use the wearable device by the user. And there are also other challenges like resource usage in terms of execution time, memory usage, and power consumption. That we will elaborate on this during the presentation more. There are other challenges like form factor, which is about dimensions and shape, cost and accessibility, durability, user interface, and so on, that we won't elaborate in this presentation. So as a use case example, the energy consumption of wearable healthcare systems in year 2022 has been 16.7 gigawatt hour worldwide, which equivalents to annual electricity usage of 5.36 million households in Germany year 2020, and equivalents to 19.42 tons of carbon dioxide emissions. And there will be a need of 113.4 million conifer trees for compensating this amount of carbon dioxide. Therefore, these energy consumption contribute to environmental degradation and shows the importance of energy monitoring of wearable healthcare devices. The objective of this presentation, therefore, is to monitor the data in terms of quality and actually clean or noise corrupted data, and also to monitor resource usages. There will be always a trade-off between data quality and resource usage that we should kind of, based on the value of one of these domains, find the most suitable approach for designing the algorithms of the wearable healthcare devices. The dataset that we have used is MITBIH dataset, which is the real-world clean ECG signals of 47 subjects. As this dataset is a clean ECG dataset, we use NSTDB noise stress test database using WFDB toolkit developed by PhysioNet to contaminate the signal with noise. After 5 minutes of clean ECG signals, we contaminate the signals with noise with a step of 2 minutes noisy alternating with 2 minutes clean signal. The noise types would be motion artifacts, including electrode motion and muscle artifact, and baseline wander. Thereafter, we segment the data with 10-second segments and label the data with respect to type of noise and SNR level to perform a noise detection and noise classification. Statistical features and morphological features using Vital SQI library in Python would be extracted. Statistical features include mean, variance, cortices, skewness, energy entropy, max autocorrelation, mean, variance, maximum of histogram, and raw RR features, which are distorted RR intervals, vector of the distances between the RR peaks in the ECG signals. Also, the heart rate variability features, including SDNN, RM, SSD, PNN50, and so on. And another category of features that we will explore are the concatenated of the previous features, as you can see here. So we perform different type of classifications, including binary classification, which is clean versus noisy ECG signals, and multi-class classification, which is a 4-class classification, and also 7-class classification just based on SNR levels from -6 decibels to 24 decibels, and also 19-class classification based on noise type and SNR levels. For resource usage, which is time, energy, and memory, we will monitor these for feature extraction per window and also per inference. Per inference means feature extraction plus feature normalization and ML prediction steps. The platform that is used is an 13th generation Intel Core i9 processor with a clock frequency of 5.6 GHz, and operating system is Linux, and we use Python version 3.10.12. And for measuring execution time and memory usage, we use timeit and trace-malloc modules. And for energy consumption, we use running average power limit available on Intel processors. For evaluation, we use F1 score and accuracy metrics, and SVM, random forest, XGBoost, gradient boosting, extremely randomized trees, decision trees. And the criteria would be leave one out, cross validation, and data balance. The results of the classification of noise is shown here for 4-class classification for different models and also different type of features. As you can see, concatenated features have achieved the best results in comparison to the other type of features, and also statistical features in most of the times have better results than RR features. And I should also mention that XGBoost outperforms the other type of machine learning models. The trend is kind of similar for 7-class classification, which was for SNR levels, and also 19-class classification. However, the accuracy results for 7-class and 19-class classifications would drop in comparison to the 4-class classification. The best results belong to binary classification, which is noise versus clean classification of the ECG signals, and SVM, gradient boosting, and XGBoost outperform the other models. For the resource usage results, as you can see here, for execution time, concatenated features almost have will take 7 times longer time in comparison to the statistical features. And for energy consumption, this trend is the same, but for current memory, the concatenated features still use the highest amount of memory, but process RR features use less memory than statistical features. And also for different type of models, as you can see here, the execution time and energy consumption for decision trees is the least, and for SVM models is the most. And the current memory consumption or usage is almost the same across different models. So to discuss the results, we could consider different scenarios. If the priority is accuracy, one would probably consider XGBoost as it had most of the time the best performance in comparison to the other models. And if we are also performing a binary classification, gradient boosting and SVM could be also good options. However, the downside would be increase in resource usage. If in another scenario the priority is resource usage, so decision tree based on the figure as you can see in the bottom would have the least amount of execution time and platform energy, and it kind of improves the execution time compared to other models 7 to 160 times. However, the downside here will be the lower accuracy. So to summarize and conclude, we kind of detected the corrupted ECG segments with different SNR levels using machine learning. So one could use different denoising methods to kind of mitigate the amount of noise and then perform the classifications. And this will reduce the number of false alarms in the wearables, or completely ignore these noise corrupted parts of the signal if the amount of noise is very high, to perform the classifications based on the cleaner part of the signals. We also monitor the resource usage for different algorithms that we use in terms of execution time, memory usage, and energy consumption to kind of introduce a trade-off between the accuracy results for classifications and also resource usage to select the suitable approach for designing algorithms for wearable healthcare devices. These are the references that I have used for this presentation, and thank you very much for your attention. If you have any questions, you can contact my email and I would be happy to answer you. Thank you very much. You can also access the paper via this link or scan this QR code. Have a nice evening.